All right, so let's talk about how we can apply equilibrium constants. So if we have the value of the Kc, the equilibrium constant, we can determine a lot of things about the reaction. So we've talked about this before, but the magnitude or how big or small the number for K, it determines which direction the reaction wants to go. So we've talked about this already, but if you want to jot this down just to refresh your memory, you can. If K is very large, the equilibrium usually ends up on the product side, okay? So big K means that the equilibrium mixture or the equilibrium is going to be on product side. It means that K is bigger than 1. Okay, so if K is bigger than 1, we're going to end up with equilibrium on the product side. And then if K is less than 1, it's going to end up on the reactant side. Okay. And how big it is will determine how much product you have relative to the reactant. So if your K is like 10 to the power of like 10, you're gonna have way more product, barely any reactant. But if it's like 10 to the power of negative 10, then you'll have mostly reactant and very little product. Okay, that should be reviewed. But any questions about that? I still don't know how you guys take this class third period in the morning. Oh. That's kind of a hard class to take in the morning too. Yeah, it's a lot of reading. I don't know. I just don't know why we start school so early. It's such an ungodly hour. Anyway, so sorry, Mr. O's little tangents. So one of the things that we can do is we can predict the direction of the reaction like we talked about. So we got a reaction right here. And what we're going to do is we're going to do an ice table right now. So I'm going to start you guys right off the bat. This is going to be the information that you guys have. I want you guys to set up an ice table, and I want you guys to see if you guys can figure out which side the reaction is going to go towards. Okay. So you got your information for your problem here. I didn't number this problem, but your starting numbers are 2 moles of H2, 2 moles of N2, 2 moles of NH3. And I want you guys to figure out which side the mixture will, or the equilibrium will lie. Sorry, you don't need to do an ice table for this one, my fault. Okay, so write the equilibrium constant equation, and then you guys are going to calculate the equilibrium constant and then figure out which side the reaction is going to go towards. Sorry, no ice table yet. Okay, so if you're confused, this is going to be your equilibrium constant expression, the formula. And so you're just going to plug in your numbers and see which side equilibrium is going to lie. Okay. So any trash is fine. Where's your baguette? Are all your breakfast foods items that start with the letter B? Baguette, banana, bread. Wait, bread. Baguette is bread. I can't eat banana, dude. It just tastes so bad. Bananas taste so gross. Regardless, ripe or unripe, not good. I know they're good for the potassium and the electrolytes, but the taste is garbage. I like strawberry without the banana. Okay, guys, so let's start plugging in your numbers. So the concentration of NH3 should be 2 molarity. Since it's 1 liter, you can just use the same number for moles. So 2 molarity, got to square that. The concentration of N2 is going to be 1. And then the concentration of H2 will be 2 molarity, and we're going to cube that. So that should be 4/8, right? 2 squared is 4, and then 2 cubed is 8, and then 1/2, which will be 0.5. Okay, so your Kc, your equilibrium constant, will be 0.5. Okay, so let's answer these questions right here. Okay, will N2 and H2 react to form more NH3? Basically, are we going to go towards the products? Yes or no? No, we are not going to go towards the products. No. And the reason why is because the Kc is less than 1. If it's less than 1, which direction does it go? To the, reactants. Okay, and so will NH3 decompose to N2 and H2? Yes. Okay, so that's one of the implications of the equilibrium constant. Okay. Any questions about that? Pretty simple, right? I don't know why I wrote this. I think it's the wrong Kc. Okay, ready to move on? All righty. So that one's pretty simple. We got that. You guys can, this is all from your book. We can skip all this. Oh, this is important. Okay, so when we take a look at equilibrium constant like this, we can use a quantity called the reaction quotient, okay? And we symbolize that with Q. And Q is a number obtained by substituting the reactant and product concentrations at any point during a reaction into the equilibrium constant expression. So basically, this is the ratio between products and reactants before they reach equilibrium. So Kc is when the things are at equilibrium, right? Kc is the ratio at equilibrium. So let me write that. So Kc, the equilibrium constant, is the ratio at equilibrium, but Q is going to be the ratio at any point, okay, given our parameter. So as long as you define what point that is, that's going to tell us the ratio, which we call Q. Okay, so Kc is when it's at equilibrium, products and reactant ratio, and Q is the ratio at a certain point that's not equilibrium. Okay. And then obviously there's a QP, and that's going to be for partial pressures rather than concentration. Okay, and if you guys notice, it's the exact same formula as the equilibrium constant formula. It's just that we're going to be doing it for the values not at equilibrium. Any questions about what Q is? So Q is when we don't know if it's at equilibrium. That's when we call it Q. Okay. Okay, so Q is very useful because it can tell us whether our system is really at equilibrium or if the reaction is really slow. So some chemical reactions take a super long time to take place. So for example, when I was in college, one of our organic chemistry lab, it's a 4-hour section. So we meet twice a week for 4 hours just for the lab. Okay, and the reason why it's so long is because some of the reactions take a long time. There was one time where we started a reaction, took us like 10 minutes to set it up, and then we had to wait an hour and a half. So we went out to get coffee, and then we came back, and then we did some other things, and then we left for another hour and a half. So I literally went to school to get coffee, which is horrendous. But anyway, the point is, some reactions take a really long time to take place. Hour and a half is honestly not that bad. Some reactions could take days, even weeks or even months to complete, to go to equilibrium. So a lot of times when people are studying these reactions, we don't know if it's at equilibrium yet, just because the reaction is so slow. And that's why we use Q. Okay, so Q is useful because it lets us tell us if it's at equilibrium or not. And so if Q is equal to K, the system is at equilibrium. So if you measure the ratios and it's equal to K, we know that it's at equilibrium. If Q is greater than K, then that means we have too many products still. And so the reaction is going towards the reactants. And if Q is less than K, then that means it's going to go towards the products. Okay, so if Q is less than or greater than K, it's going to go to the reactants. And then if Q is less than K, it's going to go towards the products. Okay, that's how we can tell which direction the system still needs to go towards in order to hit equilibrium. Okay. So just to reiterate, if your number for Q, so for example, let's say your K is, I don't know, 0.01, okay? And then you're working with a reaction. Let's say this is my flask. You got your, right? Okay, and then you measure the compounds in there. If the ratio that you get, if Q is bigger than K, it means it's not at equilibrium. We have too much product, so we still need to make more reactants. Okay, but if Q is less than K, that means we have too much reactant and we need to make more product until we go to equilibrium. Okay, so it's kind of a useful way to figure out whether our system is at equilibrium or not. Very useful when reactions take a super long time and you want to make sure if it's at equilibrium or not. Okay, yeah, what's up? Yeah, too much product. All right, make sense, guys? Okay, let's do some math. All right, so we're gonna take a look at 12.24. I'm gonna leave the Q thing right here. Let me give you a little more space to work with. Okay, so let's take a look at 12.24. It tells us that the equilibrium constant for this reaction is 50.5. So Kc is equal to 50.5. Let's jot that down somewhere. And what you want to do here is figure out which direction the reaction wants to go if we start with these these moles of these compounds in a 2-liter container. Okay, so remember, this system is not at equilibrium yet, and so we're going to be using the Q equation, but the Q equation is the same thing as the equilibrium constant equation. So it's still going to be the concentration of products, and since HI has a 2 in front of it, we have to square it, divided by H2 concentration and I2 concentration. Okay, so what I want you guys to do is calculate Q, compare it to the equilibrium constant, and see which direction the reaction still wants to go to. One thing I do want to mention though is that we have moles and liters, so you do need to convert into molarity. Okay. We're at 12.24. We're like applications of the equilibrium constant. Alrighty, guys. If you're finishing up, please feel free to finish up, but I'm going to start plugging in the numbers. I misspoke earlier. You didn't need to put in the 2 liters to find the molarity since they'll cancel out. If everything's divided by 2 liters, they'll cancel each other out. Okay, so on the top, you're going to plug in 0.02, and then you're going to square that. On the bottom, the moles of H2 is going to be 0.01, and then I2 is going to be 0.03. And so if we simplify that, we should get 1.333. Everyone got that? Okay, so regardless of whether you divided by 2 liters or not, should have still got 1.333. Okay, so this is our value for Q. We said the Kc is 50.5. So we can look at this and obviously it tells us it's not at equilibrium, right? Now the key is we need to figure out which direction the reaction wants to go in. So if we have a value that's smaller than Q on K, if K is smaller, Q is smaller than K, what does that mean? We have too much of what? Yeah, we have too much reactant. Okay. We still have too much reactant, which means that the reaction is going to go towards the products. Okay, so the reaction goes to products. Okay, and that is what this is telling us. Okay, and that's it. That's how you use Q. Any questions? Hopefully it's not too bad because we will be combining this with ice tables in the next problem. But it's not too bad. You guys told me you're good at ice tables now. I've never lied my whole life. Oh, I know you guys do. Everyone always lies to me. All right, ready to move on? All right, 12.25. Do you guys want to try this on your own without me? Okay, I'm gonna give you guys 5 minutes. See if you guys can work this out. I will let you know you will need to construct an ice table. And so just make sure you guys get on that, okay? But I'll give you guys 5 minutes. You can work with the person next to you. See if you guys can figure out what the concentrations are going to be at equilibrium. All right, good luck, guys. Okay, guys, let's start going over this. If you're still working on it, you can, again, ignore me and just check your answers. Okay, so I set up the ice table. And so I found the concentrations by dividing by the volume. And so we got 0.2, 0.2, 0.5. Okay. Now, if you guys notice, this is different from all the other ice table problems we did, because usually there's a 0 on the product side or on the reactant side, right? You either only start with product or only start with reactant. Okay, and so here we don't know what change is going to happen. We don't know if we're going to get more reactant or we don't know if we're going to get more product. And so this is where Q comes in, because Q tells us which direction the reaction is going to go, right? If it's going to go left or to the right. And so all we're going to do is find Q. So we're going to do 0.5 squared on the top divided by 0.2. And I guess we could square it because it's the same value. And so we're going to find that Q is 6.25, okay? So Q is 6.25. Now, it says here that the equilibrium constant is 129, and so Q is less than the equilibrium constant, right? So if Q is less than the equilibrium constant, which direction is the reaction going to go? Yeah, it's going to go towards the product. That means we're going to gain product and we're going to lose reactant. So that's where we figure out the change. So we're going to lose reactant. Oh, brain fart. And then we're going to gain product. Okay, that was the first step. That's how you can figure out whether we're going to gain or lose reactant or product. Okay, now if it was the other way, if Q was bigger, we would add reactant and lose product because it's going to go the other way. Okay, so we can find our equilibrium concentration to be 0.2 minus x, 0.2 minus x, and then it's going to be 0.5 plus x or 2x. Okay, and now we can solve for x. Okay, we can solve for x because we know that at equilibrium, the Kc is equal to 129. Okay, and we know that it's going to be the equilibrium concentration of HI. So it's going to be 0.5 plus 2x, coefficient's 2, so we got to square it. And on the bottom, we have 0.2 minus x times 0.2 minus x. It's the same formula as the Q, except we're using the K. Okay. So I'll stop right there. Any questions on where we plugged it in? Is it kind of starting to make a little bit more sense now? Okay, hopefully. Now, this looks like a beautiful quadratic formula that is forming, right? Okay. But I'm actually going to spoil the fun and tell you guys you don't have to do the quadratic. Because if you look at the denominator, we have the same thing twice, right? So we can actually rewrite this, boo, and then it just turns into squared on the bottom because we have the same value 2 times. And if we have the top and bottom squared, what we can do, I'm going to rewrite it real quick, but we can say that this entire thing right here is being squared, right? Because the top and bottom were both being squared, which means we can just find the square root of both sides. And if we find the square root of both sides, that means that this is going to be, we can simplify this as 129 square root of 129 equals 0.5 plus 2x divided by 0.2 minus x. So if we do that, we don't need to do the quadratic. It's just a very simple algebraic expression. All right. Any questions on the setup? Okay, this is the easy part. I think you guys are good enough at simplifying this, so I'm going to skip the long process, but you should get x equals 0.133. Okay, so this is going to be your value for x. Okay. And then from there, we need to find the equilibrium concentration, so we just plug in the values. That means that, oh, I'm going to use a different color. That means the concentration of H2 and I2 is going to equal 0.067 molarity. And the concentration of HI is going to equal 0.766 molarity. So this is going to be your final answer. Oh, that's a lot. This is fun, right, guys? Don't you love chemistry and love math? Yes. You're definitely going to need this if you don't go into chem on an everyday basis. Right, but that's how we can use Q to determine how we're going to go to equilibrium. Because if you think about it, a lot of times you're not going to only start with just the reactants, right? You're going to have reactants and products in there. And then we got to figure out which way it'll go to equilibrium. Okay, so I'm going to give you guys a choice right now. Do you guys want to take your break now? Or do you want to do a big problem and then take a break? Big problem? Big problem first? Okay. Wow, you guys are scholars. Okay, let's do a big problem and then we'll take a break. So you guys know how to use Q now. And so now I'm going to have you guys try 12.26. Here, Mr. O doesn't even give you the reaction. So you got to write the reaction too. Oh my gosh. Okay, so I'm going to give you guys about 7 minutes to try this out on your own. You're going to have to do literally everything on your own, kind of throwing you in the fire again. But again, try it out. I'll put up the reaction in about a minute or so, just so that we're all working on the same reaction. But you're gonna have to do all the other steps that we talked about. This is similar to the previous problem, just a little bit more work. Okay, so 7 minutes. I'll put up the reaction in just a minute so we can double check. All right, good luck, guys. Okay, so I set up the ICE table for you guys. So you should have found the concentrations for the compounds that we're working with, and this is what I got for the 3 involved compounds. Okay, now if you notice, we start with concentrations for reactants and products, and so we got to figure out what the change is. We got to figure out if we're going to gain reactant or we're going to gain product. And so in order to do that, we need to calculate Q. So this is the formula for Q for this reaction. I plugged in the concentration, then got 0.833. It tells us here that the equilibrium constant is 0.68. And so you guys can tell that Q is greater than K. And so if Q is greater than K, which direction does the reaction shift? Yeah, to the reactants or to the left. So it's going to go to the left, like Beyonce said. And so we're going to gain reactant and we're going to lose product. Okay. Oh man, I see the pain in people's faces already. Okay, so equilibrium concentrations will be these values. Okay. All right, so far so good? All right, so what we're gonna do now is we are going to use the equilibrium concentration or constant equation. We know that it's 0.68, and that's gonna be equal to the concentration of the products, 0.004 minus X divided by 0.08 plus X, 0.06 plus X. Now, this problem is a pain in the butt because we can't do that useful trick we used last time with just finding the square root. We have to distribute the denominator. And if we distribute the denominator, we are going to get a horrendous quadratic. Okay, so I'm going to simplify it. Maybe I'm going to go a little bit quickly. If you have any questions on a step, let me know. But I'm going to simplify the denominator and multiply it with the left side. And so on the left side, we should get 0.68 times 0.0048 plus 0.14x plus x squared. And that's going to be equal to 0.004 minus x. Okay. And so if we simplify the quadratic so that it equals 0, you should end up with 0.68 x squared plus 1.0952 x minus 0.000736 equals 0. Okay, our numbers might be off by a little bit, maybe rounding errors, but this is what your quadratic should look like. Let me know if I made any mistakes. Okay, but what you should have done is you should have distributed 0.68, and then from there just transfer this to the other side. Did I mess up somewhere? Just want to make sure. Because, you know, I make a lot of mistakes. Good? Wait, what? Oh, you got a negative number. For which one? Oh, okay. That's interesting. Let me check your math during the break. I'll see what happened.
No, I did something similar.
Okay. Yeah, what's up, great? Uh-huh. Because you got to multiply the 0.68 with 0.0048, and then you subtract 0.004, or you subtract that 0.004 from it. Yeah. I think you, yeah, because it's switched right here from this side. Yeah. So you do 0.68 times 0.0048, and then you subtract 0.004 from that. Let me double check my math to make sure we're on the same page. 0.68 times 0.0048 minus 0.004. Yeah, and then you'll get negative 0.000736. Okay, we're good. Last call to correct Mr. O for a free A. Just kidding. Okay, so now we're gonna plug this into our quadratic formula. So for quadratic, we'll do our great song, x equals negative b plus or minus the square of b squared minus 4. It's harder to do this while you're writing. AC 0, 0, 0, 0, 0, 736. AC all over 2A. Okay. Yeah, sorry, I'm like running out of space here. But if we simplify this down, we should end up in a place where we have two options. We're gonna come to a place where we have x equals negative 1.0952 plus or minus 1.0961 divided by 1.36. So everything in here inside the square root should give you 1.0961. And then we got b, and then 2 times 0.68 is 1.36. Okay. And so our two options are going to be to add or to subtract. I think you guys see what's coming. But if you end up adding, you're going to end up with x equals 0.0009 divided by 1.36. But if you subtract, you're going to end up with x equals negative 2.1913 divided by 1.36. And obviously, we cannot get a negative number, so we're going to want to add. Okay, so x is going to be equal to 0.006618. Okay, we can rewrite that in scientific notation. 6.618 times 10 to the power of 1, 2, 3, 4, negative 4. This is going to be our value for x. All right, I'll pause right there before I give you the final concentration answers. You guys all look kind of depressed now.
Do it.
But same thing as before, we're just gonna plug it into this equation, right? Or into our equations, and that'll give us our final concentrations. So for our final concentrations, we will get, for the concentration of carbon monoxide, we will get 0.08067. The concentration of bromine gas, we are going to get 0.0607. And for the concentration of carbonyl bromide, COBr2, we are going to get 0.00334. And this is it. Oh, it's a lot. Yeah, what's up, great? The quadratic equation? Yeah. Give me 1 sec. I'll put it up on the screen after we go over this. You want me to sing it? I have a guitar over there. Should I play guitar too? No.
I'm gonna play A, B, and C chords.
No. Yeah, only A, B, C. That'll sound so bad.
You can make it work.
No. Okay. We do have this recorded, so don't freak out, and I'll put this back up. But let's take our 5-minute break. If you need to go to the restroom, go to the restroom. And yeah, we'll be back to finish up for today. So we're gonna do 12.27. But before we do that, I do want to give you a little bit more information. So this is just basically telling us that the equilibrium constant, we can use it to find the reactant and product concentrations at equilibrium. Basically, we use the equilibrium constant to use to create ice tables. So I want you guys to take a second, and I want you guys to solve 12.27. It gives you a reaction up here and the equilibrium constant for partial pressure, and it gives you the partial pressures of H2 and N2. And I want you guys to find the partial pressure of NH3 at equilibrium. So I'll give you guys about 4 minutes to do this one. This one should be pretty quick. make sure you guys read it carefully because you could skip a lot of steps. Okay, good luck, guys. Okay, so for this problem, if you guys did a full ice table, you did too much work, like I mentioned. What you really want to do is read the problem carefully and to make sure you guys didn't do extra work. Okay, it tells us that this is our reaction. But if you guys take a look at the partial pressures are at what? Is it at the beginning of the reaction or is it at equilibrium? Yeah, it's already at equilibrium. It says when it's an equilibrium mixture of the three gases, H2 is going to be 0.928, N2 is going to be 0.432, and it's asking us the partial pressure of NH3. So you guys did not need to do an ice table for this. All you had to do is you needed to use the equilibrium constant formula. So we have the value of Kp already. So 1.45 times 10 to the negative 5. That's going to be equal to the concentration of NH3. I'll say that's X squared divided by 0.432 and 0.928. So this is your formula. Okay, so again, be very careful when you guys are reading the problems to make sure you guys didn't do any extra work. Yeah, do you have a question? Oh, yes, thank you. Great catch. We should switch places. You can teach the class now. Yeah, so third power. Thank you. Good catch on that. All right, so if we simplify that out, X is going to be equal to 0.00224 ATM. And that's it. Oops. All right. Any questions? So again, be very careful about what all of the numbers mean. I know that when we see, a reaction and we see equilibrium, we're like, oh, like we got to use an ice table. And a lot of times you will, but if it tells you the equilibrium concentrations, you basically don't need to do any work because it doesn't matter where we started or how much it changed because we're looking for the value at equilibrium. And we already have that. All right, we're going to finish up with 12.28, which will be our last problem. So let's move on to 12.28. Okay, but in a lot of situations, we know the value of the equilibrium constant and the initial amounts of all the species. Okay, we just solve for the equilibrium amounts from that. Okay, and this just means that we need to find the change in concentration. So basically, this is telling us that when we do ice tables, make sure that you guys keep track of the coefficients, okay? If it's a change of 2 moles, you have to do minus 2x or plus 2x. If it's 1 mole, we do plus or minus just 1, okay? So just make sure you're careful with that. But anyway, with that being said, so when you do change, right, you have to keep in mind the coefficients. That's all it's saying, because that's what this is. It's a long way of saying that. Look at the stoichiometry.
But is that the weird formula where it's like 1 over the thingy?
Anyway, let's do 12.28. Just letting you know this is gonna be pretty straightforward ice table. So try it out. I'll give you guys about 5 minutes and then we will go over it. And this will be the last one for today. Good luck, guys. All right, so for 12.28, I set up your ice table for you. You didn't really need to divide by the volume because it's 1. So the concentration is gonna equal the moles. So 1 molarity H2, 2 molarity I2. We don't have any HI in the beginning. You want to keep track of the stoichiometry. So we're going to do minus X for the reactant since it's 1 for each coefficient. The coefficient for HI is 2, so we got to add 2X. And so what we got are the expressions for the equilibrium concentrations down here. 1 minus X, 2 minus X, and 2X. And so what we're going to do is we are going to plug in these values into the equilibrium constant formula. And so that's going to give us 50.5 equals 2x squared, 1 minus x on the bottom times 2 minus x. Okay. And so from here, you guys know that we are going to need to use a quadratic to solve this. And so I'm going to skip a lot of steps right now for the sake of time. We're going to end up with 46.5 x squared minus 151.5 x plus 101 equals 0. And that's going to be our quadratic. So if you simplify this, this is what you should get. And I am 99.9% sure this is correct. Might be wrong, but Elaine is nodding, so now that's 100%. That gave me the extra confidence I needed. Okay. All right. And then we would plug that into the quadratic formula. So x equals negative b, so 151.5. Since it was negative 151.5, we gotta go positive. Plus or minus the square of b squared. So negative 151.5 squared minus 4ac all over 2a. Okay. And so we are going to simplify this down, and the two answers that we can get are 2.323. We can also get an answer of 0.935. And so if you guys notice, these are both positive numbers, right? So we have to test both of them. Now, out of the two, which one do you guys think makes more sense, 2.3 or 0.9? Yeah, 0.9, because if you notice, what do we have to do here? 1 minus x. If it's 1 minus 2.3, it's going to be a negative number. That doesn't make any sense. So your x value is going to be 0.935. So x is equal to 0.935. Okay, so the final answers here, if we plug in these values, the concentration of H2 is going to equal 0.065 molarity. Concentration of I2 is going to equal 1.065 molarity. And the concentration of HI is going to equal 1.87 molarity. And there you go, your final answers. Woo! All right, guys, we did a lot of quadratics today. Hopefully that wasn't too bad. Again, this is recorded, so if you guys want some more practice or if you guys want to go back, these are good problems to try again. So if you guys want to get some more practice in, make sure you guys look at these. Other than that, that's it for today. Great work, everybody. You'll be dismissed when the bell rings.